So, we have a scatter plot. Let's say it looks something like this. The regression line, again, it's not going to go through every point, but it's going to be a line that best fits the data. Okay? And I told you that it's a linear line, like our y equals mx plus b that we're used to from college algebra, but the formula is a little different. Instead of writing it like this, for the regression line, we write y equals b sub o plus b sub 1 times x, but it's basically the same thing. All right, and we had talked a little bit about error, I believe, not a whole lot, but we talked a little bit about that, this line is not going to go through every point. It might go through 1 or 2 points, but there is an error, say from this point right here. There's an error because this is what we would predict that it would be that's on this line. So this purple point here, that's where we predict when x equals this, and y equals this, we predict it's going to be there, but it's actually not there. It's up here. Okay? So there is a margin of error there. And there's a margin of error between every point. Unless the line goes exactly through the point, every one of those little black dots up there, there's some little margin of error. Okay? And that margin of error is actually important. We want to calculate that margin of error once we can figure out the regression line. Or it has a couple of names. But once we figure out that line, it's important that we calculate that margin of error. Because it does have some meaning to us in statistics. All right, let me show you an example. So I'm going to pull up a table real quick. Let me see if it is on your PowerPoint. Yes, it is. If you look, so we're on PowerPoint for section 5.2. If you look at the back page of, page 2, we're going to look at that chart there, that XY chart. Give me just 1 second while I pull this up so you can see it a little bit better, and I can see it a little bit better. Alright. And of course, this is a pretty small data set we're looking at. Just like anything else that we do, the larger the data set, the more calculations are going to be. Alright, whenever we start figuring out these lines. Alright, so if we have this data set, again, that is in your PowerPoint. And let's say that we were to graph that data set on a scatter plot. Now, even though you don't know how to find the regression line, I am going to give you the equation of that, and then after I go over this example, I'm going to show you how to find the values of the line. So if we were to graph this, you can see it's in the next slide there. So this, I guess it's a light blue, bluish greenish line. This line, this is the regression line. And again, you don't know how to find that yet. Here's the equation. So here's b sub o right here, that first number, and there's b sub 1 right there. Okay, that's in front of x. And you can see it doesn't go exactly through any point, but it is the best fit of any line that we could possibly come up with. Okay, and you can see that it does predict what values that we get out. It just doesn't exactly predict the values that you get out whenever you plug in an x. For example, look, if I plug in a 2 right here into this equation, then my predicted value is whatever I get when I plug in a 2. So let's go through each value for x, or for each point. So this is the point 2, 3. The predicted value is what? So if I plug in a 2, it's going to be 1 plus 0.7 times 2. So that's 1 plus 1.4, or 2.4. Right, so the predicted value at this point when x equals 2 is 2.4. All right, but what is, and I can just put the x values here. I'll just put the x values. What is the observed value, though? What is actually there? Well, what is actually there when x equals 2? Y is actually equal to 3. All right. So, do you see how I can get a margin of error now? The margin of error, or the error that we're going to use, or that we're going to find, is always going to be the observed value minus the predicted value. So it's what it actually is minus what we get if we plug in a 2 into our regression line. So that would be 3 minus 2.4, or what? So I'm going to have to write a little smaller. 3 minus 2.4, or 0.6. All right, that's our error. It's not real. I keep saying margin of error, but that's our error. Just call it error. All right, now let's look at the next x value in our table. That was 4. So for 4, where does the predicted value come from? It's always going to come from the equation. So if I plug a 4 into my equation, then I'm going to have 1 plus, do I need to write that down? Do y'all? Okay. All right, so let me plug in a 2 right here. 1 plus 0.7 times 2. That was 2.4. Getting it from this equation right here. So if I plug in a 4, that's 1 plus 0.7 times 4. What the regression line does is it predicts the values that we could get. All right, it's the best fit line, but it predicts the values that we could get. So the prediction here is that when x equals 4, y is equal to 3.8. So the predicted value is 3.8. Well, what's the actual value? That's called the observed value. If you look at the at the point, you don't even have to have the table to find the observed value, or you don't have to have the graph. You can just look at the table. You know, this says when you plug in a 4, you get out a 2. Or if you look at the graph here, when you go to x equals 4, the actual value, the observed value, is 2. So to find the error, I wonder if I can make that a little bit bigger here. I'm going to write this smaller. Observed. So to find the error, we're going to say the observed value, which was 2, minus the predicted value, 3.8. So that's going to be negative, what? 1.8. Let me write that again. Okay, and I can do that for every value in my table. So if you look at your PowerPoint in the bottom right, that's what they're doing. That's what that table is. Bottom right table of your PowerPoint. They do that for every value. They do that for, here, let me see. If the homework asks you to find the error, this is how you find it. Yeah, well, there's a lot of other stuff that we can get from this, but if it asks you for the error, there's a certain name we can call the total error. All right, and I'm going to show you how to do that. So the other ones are, let's see, what are the other x values? So we got 5, 8, and 9. So 1 plus 0.7 times 5, take my word for it, that's going to be 4.5. And 1 plus 0.7 times 8, that's going to be 6.6. And 1 plus 0.7 times 9, that's going to be 7.3. All right, so those are all predicted. Those aren't actual values, but if we just had that line, we could predict what we would get out. You know, kind of like we went over, there was an equation that we had for hours studied and the grade you would make on the test. I mean, it wasn't exact, but it gave a prediction of what you would make on the test if you studied for 10 hours or something like that. Well, that's what we're doing here. We're looking at predictions. Now, what's the actual? The actual is called the observed value. Okay? So the observed value is the actual value you get from the table or you get from the scatter plot. So when x equals 5, y equals 6. When x equals 8, y equals 5. When x equals 9, y equals 8. And so the way that we find the error is we always say the observed minus the predicted. So this one would be 6 minus 4.5, or 1.5. All right, and then what? 5 minus 6.6, that's negative 1.6. And then 8 minus 7.3, that's 0.7. Now, if we sum all of those up, then that's the sum of the error. So if we add all those up, so we add up 0.6, negative 1.8, 1.5, negative 1.6, and 0.7. If you add all of those up, you get negative 0.6. And of course, we would want the smallest error possible. The smaller the error, the better the line fits. Okay? There's also another value called the square of the errors. It's called the sum of squared errors. The sum of squared errors. And it's just like what it sounds like. You take each error and you square it. So why would that be good? Because some of the errors you notice were positive and some of the errors were negative. So it's kind of like some of them canceled each other out. But if we square each error, then we're going to have a value that will be positive. And it's a better way of measuring the total error. Okay? So the sum of squared errors, you take each error and square it. I don't have enough room up here to make another column. I'm going to make it down here. All right. I'm going to name it error squared. That's what your book calls it. And I don't know how they just probably just put the square there without a parentheses. Now if you look at the table, it's kind of hard to see those little numbers. But if you look at the table, you can see what they did is they took the value and they squared it. They took each error and squared it. That means that everything you get out will be positive. Alright, so when I square the first one, for x equals 2, they got 0.36. For x equals 4, 3.24. For x equals 5, 2.25. For x equals 8, 2.56. And for x equals 9, 0.49. Again, why is that a good value for us to look at in the real world? That's a good value for us to look at because some of our error was positive and some of our error was negative. So if we just take the sum of our errors, then some of those negatives and positives are canceling out. So that doesn't give us a real good read or a real good feel to how good the line is actually fitting. But if we square all of those values, we make them all positive, and then we find the sum of all of that, that gives us a value that's a better representation of does this line fit or does it not fit that good. Okay? So if I take the sum of all of those values, the sum of the error squared, I get 8.90. Now, your book gives a formula for figuring it all out, and it's actually what we did, but the formula makes it look a lot harder than it actually is. I'll show you the formula just so you can see it and you'll know what it means, because it really wasn't that hard to find the error and then square it and take the sum of all that. But if you just need a formula to go by, here's the formula. And they call the sum of squared errors SSE. That's the sum of squared errors. So remember what this was. What was this? Do you remember? That would be the observed value first. So that's the observed. And in my mind, I think about that like that's the actual. And then this right here, that is the predicted value, and that comes from the equation of the line. The regression line, or it has another good name too. Alright, and so right here it just tells you, hey, this is what you're doing. It's just another way to write it. Again, it looks a lot more complicated when you start looking at the formulas. But if you look at the example, it's not too bad. Alright, so if you were to find the sum of squared errors for multiple lines going through a set of data, whichever one had the smaller, whichever sum of square errors is smaller, that's the best line. The smallest of all lines. So if we figure out a line, if I show you an equation, how to figure out this great line that's going to go through the data, it's guaranteed that that line will have the smallest sum of squared errors. All right. I know it doesn't sound like a big deal, but I mean it is if we're trying to predict values. If we're trying to make predictions into the future using a set of data, the line that we use to represent the set of data to predict values needs to be the best line that is the closest to all the points. Okay? And so that would be the line that has the smallest sum of square errors. Another name for that line, that best line, the best line, is called the least squares line. So that's another name for it. Because it has the smallest sum of square errors. Sum of squared errors. Now, why can't we just use the errors? Because again, the errors, some of them are positive and some of them are negative. And if you add them all together, the negatives and positives cancel everything out, cancel stuff out. Okay? So it's important to have a value. If we're going to start comparing different lines, it will be important to have a value that has the smallest, it will be important to have a value that doesn't consider positive and negative values, just considers positive values. All right? And so to do that, we simply square each value. All right, now, has anybody ever heard of, probably not unless you've studied mathematicians or had really good algebra in high school, Carl Gauss, G-A-U-S-S. He actually come up with a formula to figure out this least squares line. All right, one time you may have heard of him. There's something in algebra when you start going over matrices called Gaussian elimination. So you may have heard of him then. You may have actually done some of his math and never known that you were doing his math. But several hundred years ago, he come up with the equations to find the slope and y-intercept, the m and the b, or in our equations, the b sub o and the b sub 1. Okay? And so they look a little daunting. They look a little complex. I mean, it's not real easy to figure out these formulas, so they had to be kind of complex. But if you look at the bottom of page 3 of your PowerPoint, you'll see the two formulas for the slope and y-intercept of the least square line. Notice that you need b sub 1 to find b sub o. So I'll put the box up here just so you can see it, but it is on the PowerPoint. So if we have a small set of data, we could use these to help us figure out that least squared line to find the b sub o and b sub 1. Know that there are ways in calculators or in Excel to figure this stuff out. I mean, we all know what an x is. We all know what a y is. So this is x times y, the sum of x times y. We've done that. You know, here's the sum of x, here's the sum of y. Just know that's the product of those two. You know, this is the sum of x squared, so you'd have to have an x squared column, and then take the sum of all that. And this is the sum of x. squared. All right, so it's not too bad, even though it looks kind of bad. It's just a lot of number crunching, a lot of calculations. Now, again, in Excel, I showed you how to do a little bit. So let me put the values from that table in Excel and remind you how to use Excel to find our B sub O and our B sub 1. Okay. I'm just going to need these values. So I'm going to type these values in Excel, and then I'll bring it over and show it to you. 2, 4, 5, 8, 9. Okay. So I typed those values in Excel. All right, and then I'm going to select those values, and I'm going to put them in a scatter plot. So if you go to Insert, you look at these recommended charts. You can see that one right there is a scatter plot. Let's do a scatter plot. All right, so there it is. Now, if I want to display the least squared line, I have to add an element to the chart. I have to go here, go down the trend line, and I'm going to put in, I think I can just go straight to more trend line options. Let's see. It may or may not let, okay, so put in the linear. See, that's the line. I want to see the equation. Okay. So it looks like what we were working with, and let me see if I can change the font here to make it bigger. You know, you saw what the equation was in the book that it used. You know, of course, things were rounded. Let's see, font. Come on. A little bit bigger. So in the book, we were using what? The first that equation we wrote down, it was y equals 1 plus 0.7x. So they were using rounded values. Okay, that's 1 plus 0.7x. If you round the y-intercept to 1 and you round the slope to 0.7. All right, of course, we would have to look at the directions to see what to round those to. So which one of these is my B sub O and which one of these is my B sub 1? So this one right here, that's my B sub O, the 1 point whatever. And then my B sub 1 is right here. It's the slope. Just know that it's generally written the other way, like this comes before that. So it's not hard to find the value using Excel. Has anybody tried this in their cell phone? Not in a cell phone?
I tried to do it like in Excel with my phone.
Mm-hmm.
And it didn't have the option to, like it had the design, chart design, but it wasn't like you just put the line or whatever. You couldn't have it. So you couldn't figure it out. I ended up figuring out how to do it on calculator, but.
Okay. I guess I would have to see how it looks on your computer. You know, did you select the data? Did it just didn't have this? Or?
It had that, you could do a scatter
Okay.
plot or whatever, and it pulled up the scatter plot, but it didn't have a way to like, see how yours says design and format?
Yeah.
It only had the design button, so you couldn't like find the,
Okay.
you couldn't add a chart element and insert the.
So there has to be some way to turn this tab on. I just don't know how. If it's not showing. So, did you use a laptop or a desktop or? Okay. So, yeah, if you're having that issue, let me know, and I'll try to figure out your problems. But it's under trend line options. That's where you're going to get to where you can go down and change that. But so maybe if you go to the help and you just search for trend line option or trend lines, it might help. I don't know. But I know for me to get to it, I got to go to trend line options and then scroll down and click display equation on chart. It did it again. You can also display the R squared value. So that's something that we're about to go over. All right. So there's another example in the book. I'm going to throw it up here. We're going to look through it real quick just to try to help solidify these definitions and hopefully help our understanding of what we're actually doing. So something that most of you probably haven't had to do yet, because you probably had somebody do it for you. Some of you may have already done this, but has anybody in here ever bought a vehicle? Probably not. Maybe. You know, when you buy a vehicle, as soon as you drive it off the lot, there's a huge loss in the value of the vehicle. That's very sad, but it is. And then as your vehicle ages, what happens? The value of your vehicle goes down. So, here is a chart that lists the age of this Honda Civic LX sedan, the asking price. So it's a table that has two columns here. So it's just, here's the age and here's the asking price. So of course we have, you know, multiple people selling this vehicle. That's how old it is. And so all the way down to 6 years old. Okay. So if we did calculate the slope and y-intercept with this data, here's what we would get. And you don't have to use Excel to do it. You can crunch the numbers. I know some people are like, shoot, I'm not doing that. Well, with a small data set, you can do it. You can crunch the numbers pretty easy. But if it's a large data set, this would take a little bit longer. But if you did crunch the numbers, you could figure out that your B sub O, or the y-intercept, is this number, and your B sub 1 is this number. Now, this is going to be what? Y equals, what do I write first? B sub O. So $19,198.32 plus, or actually it's going to be minus because that's a negative slope, minus, which makes sense because each year that you subtract, you know, if X is the number of years, each year that should make the price go down more. All right. Now this gives us predictions. This doesn't give us actual values. If I plug a 6 into this, I'm not going to get one of those numbers from the table. The numbers from the table are the observed values. The numbers that we get out of the formula, those are the predicted values. Yes?
So, in order to get those numbers, like the B sub O and 19,000 or whatever, you use the formula and you decide what to do?
Yes. You would use these formulas or type it in your calculator or use Excel. But using these formulas with that many data values is going to take a little while. All right. So if I type these into Excel, these two data sets, you know, the age of years, that would be my X values, and the asking price, that would be my Y values. All right, and I got it to graph it and come up with an equation, which we just came up with the equation. It would probably list the X value first, just like this figure I'm about to put up here. All right, it wouldn't look this pretty, but it would look something like that. And it would give us the equation. This is the scatter plot. So it looks like that line is pretty closely fit there. Well, what all could I get from that line? I could figure out the error. I could figure out the sum of squared error. Let me show you the table. I'm going to show you another table. This is a table where all that's been done. And more than likely, if you were doing a homework problem, even if you get the equation, if it asks you for the sum of square error, that equation doesn't give you that. Okay, you need the equation to figure all that out. So here's the table. So you know, use the technology to get the equation, this equation right here, and we have all of the observed values here. That's the Y values. To find the predicted values, we have to plug in this number into our equation. So we have to plug a 1 in to get the predicted value. You see, you plug a 1 in the equation right there, you get this. That's why it's the same thing here and here. Because if you plug a 1 in, you get the same answer. You plug a 2 into the equation, you get the same answer for all three of those. And you plug all those numbers in, that's what the equations give you. Then to get the error, what do? You say the observed price minus the predicted, or the predicted minus the observed? Observed minus the predicted. So then you can see, here's all the errors. Then you can see, here's all the errors squared. And if the problem said, what is the sum of squared errors, and you had to figure that out, there it is right there, the sum of squared errors. It's a really big number. But this is the best, or it's the regression line, but it's the least squared line. All right. Is there any questions?
Is there any way to add those numbers up in Excel, or those are the ones you just have to do in the calculator?
There is a way to add them up but you have to type these in. And there might be a way to actually there may be a function to call that. I just have never done that with Excel. But I know if you type them all in, you can just select them and then hit sum. So you can go, like, I know these aren't the numbers, but let's say these were the numbers. If you select a column, so let's say I selected those. There's a button over here for auto sum. You can take the sum of the numbers and it'll put it right there. So if you do type all those values in, then you can just select them and hit sum and it'll do it for you, like a little built-in calculator. So that finishes 5.2. 5.2 generally gives students some issues because, I mean, what do we have to do? We have to be able to find those two values, the b sub o and the b sub 1, and then we have to be able to find the error and the sum of squared errors, and sometimes that takes a little while. Now, doesn't mean that there aren't easier ways to do that. Technology will actually, you know, there are some programs that can spit all this stuff out for you, but I'm not going to require you to use those formulas. Just know you can do this out by hand, even though I wouldn't suggest it unless you have to. All right, now I'm not going to give you a homework on 5.3, but that doesn't mean 5.3 is not important. We're just going to go through it really quick. So I'll pull your textbook over here and we'll look through it, even though you have the PowerPoint. Let's see. All right, evaluating the fit of a linear model is what this is on. And first starts off talking about the importance of errors. So it says the usefulness of a regression model depends on the magnitude of the prediction errors you expect the model to produce. So you might see an equation like this in your homework where it has b sub o plus b sub 1 times x plus e, or plus error. All right, well, we know what the error, we can figure out the error, but we usually don't write that in there. But the error, you know, is important. Again, it helps us figure out if we take the error squared, it helps us figure out the least squared line, or knowing if our line is the least squared. Some statistical softwares will spit out like all of those values for you. There are lots of statistical softwares that cost thousands of dollars. In graduate school, a lot of people use one called SPSS. Don't ask me what it stands for. But it's one of those things where the site license costs so much that they let you do like a temporary membership to it or something for $100 or $200 or something like that, because it will do so much. All right, some of the other values that you can get out. Let's just look at this real quick. Let me see if I can scroll over. It's not wanting to cooperate with me. The variance of the error. Everybody knows what variance is? Hopefully by now. Just the standard deviation squared, but you can see down here in the left-hand corner the variance of the error. It's on your PowerPoint. It's actually just equal to the sum of squared errors divided by n minus 2. It's just a shortened formula to be able to find the variance of the error. So you do have to find the sum of squared errors. That's what this stuff up here is. It's just another way to write it. And then you divide it by n minus 2. All right. A lot of this stuff we haven't really got into yet, like this df right here. Coefficients. That's the coefficients from the equation. The regression equation. Don't worry about any of this stuff here. But you can see they list the standard error, the number of observations that were in the table, multiple R squared, adjusted R squared. So I mean, there's all kinds of values that you can calculate. We're just going to stick with the basic ones though. The coefficient of determination. Let's read through this. It says the goal in constructing most linear models is to use the independent variable x to explain or predict the dependent variable y. The question we want to consider is how much of the variation can be explained with a model. Okay. Before determining how much variation the model explains, it will be necessary to evaluate how much variability exists in the y value, or the y variable. This quantity is called the total sum of squares, total SS, and represents the total variation in the dependent variable y. So look at the actual variable here. Let's see. I have to go back. So the total sum of squares, total SS, you can do it. Alright, this thing's kind of squirrely. No offense to squirrels, but it's a little squirrely sometimes. It's in your PowerPoint as well. So let me find it. Yeah, the total SS there was given. Total sum of squares. It says is y minus y bar, the sum of y minus y bar squared. There, that looks a little better. We have this r squared right here, though, the coefficient of determination. We've already seen the little r. All right, this is another value that can be formulated, though, once we have the sum of squareds error. So to do that, though, we have to say 1. Now look at the formula. It's on your formula sheet. 1 minus the sum of squares error divided by that total sum of squares. Since it's r squared, it's not going to be negative. It's going to be positive, and it's always going to be between 0 and 1. So that's not the exact same as the correlation coefficient. All right, that's called the coefficient of determination. All right. This is kind of neat down here. I think this is in your PowerPoint. The numbers are kind of small, but it shows SAT scores and graduating GPA. Of course, SAT wants these values to be good. You know, the better you make on your SAT, they want you to, I guess they would want the students to show that the better their GPA would be. That's not always the case. Yeah. Let me see, I might just be able to clip that out. Let me bring it to my other monitor for a second. My other monitor seems to do better. All right. So here's the table. All right, so here's different students, what they made on the verbal part, the math part. There's their total SAT scores. Anybody here taking their SAT? I have one student in one of my classes tell me they took it. Can't remember what they made. I think it was like a 1250 or something like that. Perfect is 1600. Is that right? I think so. Not 100% sure. But so you see SAT scores, college GPAs. There is an actual line, least squared line, that can be figured out to predict the GPAs according to their scores. All right. So here's the predicted GPAs. Here's the error. Here's the error squared. So you can see sometimes the predicted GPA is off a bit. If you look, let's see, not sure if it's on your slides or not. Probably not. But you can see, let me see if I can pull up the scatter plot for you. So here is, hopefully pulling this over doesn't mess anything up. Maybe it'll still stay the same size. So here's 30 students and their GPAs. Here's the scatter plot. I could guarantee you there's going to be a pretty big margin of error there, because think about the line going through this and see how far some of these points would be away from that line. So that's going to create a pretty large margin, or pretty large error there that would create a pretty large sum of errors. All right, and look at the, see if it gives us the variance, the standard deviation, which for GPAs, that's a pretty big standard deviation, pretty big variance. Now, if you want to do the coefficient of determination by hand, check out the formula. Maybe. Might have to zoom back out. So, what is this formula though? Dadgummit, it just won't come up right. Let me zoom in. I know I'm boring some of you, so I'm going to try to move on pretty quick. You've seen this formula. I know you don't go home at night and study these formulas, even though that would be a very fun night. But we talked about this formula in the last meeting. This is a version of the formula, because there's only one thing different. There's a square there. What is this the formula of? We actually worked out a problem and used the formula. Y'all killing me. Don't break my heart. Yeah, the correlation coefficient. So it's just a correlation coefficient squared. So if we wanted to know the correlation coefficient and we had r squared, we could take the square root of r squared and get the correlation coefficient. Alright. That was the big reveal. So now we're going to move on to 5.4. 5.4 is a relatively short section. This is the last regression section that we're going to cover. Fitting a linear time trend. All right, so what would that mean? What is time trend? You would think about maybe time changing, right? Looking at data over time instead of just the X value being somebody's SAT score and the Y value being their GPA. So this is looking at data over time, something that I have struggled with my entire life, is related to this chart here, weight. I have been anywhere from 310 pounds in my adult life to 205 pounds in my adult life. So I'm diabetic and my weight does yo-yo. Of course, I know the better I eat, the more I exercise, the better shape I'm going to be in and the less I'm going to weigh. And the better my diabetes is going to be under control. But I'd say over the last year and a half, I've been back on that upswing. I've probably gained 30 pounds in the past year and a half, 2 years. And so I'm trying to do things now to help my life so that I can live longer, so that I can be there for my family. But it's something that a lot of people struggle with. A lot of freshmen struggle with, a lot of sophomores. Get to college, it's real easy to eat those ramen noodles and all that fried food in the cafeteria and but a lot of people struggle with that and deal with that. And so you can see here is a percent of overweight American adults. It's very high. It's bad. I mean, this is serious. And Mississippi is one of the worst states. We have like one of the highest percentages of obesity in the nation, which would mean, since we're the fattest country in the world, or I don't want to use the word fat, I guess obese, we're the most obese country in the world, then we are probably one of the most obese places in the world here in Mississippi, or at least percentage of people. And so you can see as time has moved on, I'm sure if you went back to the 1950s, and I'm sure it would just keep going down and down and down, because now would it continue and go down to zero eventually? Probably not. But it would get a lot lower. So using this model here, things don't look good for us in the U.S. If things continue to go like they do, then we will have more and more problems with weight. And, like I said, this is something that's affected me my entire life. So it's something that affects a lot of Americans, or a lot of adults, period. All right. So there is computer software that can spit out, all these different things, the coefficients, the error, the R squared and all that with this same type of data. There is actually an equation. Here is the least squared equation for this set of data. It will be y equals negative 705.5214 plus, this is to estimate the percentage, plus 0.3851 times the year. So what do you think the year is going to be in my formula? That's going to be the x. Now that's our x value. Okay, so if you plug in a year, according to this, we can see what the percentage is predicted to be. So let's see by the year. See, everybody in here is probably 20, early 20s. Let's say about 10 years from now. How about let's just say in 2030 what this would predict. Now in 2030, most of us in here, not all of us, but a lot of us, a lot of y'all are going to have kids, you're going to have a family. What's the percentage according to this in 2030? My daughter graduates high school in 2029. So, this would be a good, how is America going to look in 2030 whenever she starts college? So it'd be y equals negative 705.5214 plus 0.3851 times 2030. So let's do that. Let's do it. All right, 2030 times 0.3851 minus 705.5214. So according to this model, about 76% of American adults will be obese by that time. Let's hope that that doesn't happen. Let's hope that that people take better care of themselves. So everything that we've been doing can be applied to data over time as well. I mean, predictions are important. Predictions are very important. Do you know who likes to see that data? Pharmacy companies love to see that data because they're going to be making lots of money. right? For better or for worse. There is something in your book. It's not, I didn't hand out the PowerPoint, so you probably won't see it unless you go to your book. There's like a little review page for formulas. I know that when you're online doing all of that, you know, it's pretty easy to get the formulas. You see this key formulas? It may keep, yeah, it keeps going. So we have these key formulas over here. These are just the formulas that we've covered so far for least squared line and all of that. See, there's the slope, that's the piece of 1. The sum of squared errors. To me, it makes more sense looking at tables, but the formulas will give you the same thing. See, that continues here. Can't pull this down, but that top equation there is the mean square error, and then we have the standard error, the total sum of squares, total sum of regression, the coefficient of determination, which now you can see they're right on top of each other here, side by side. You can see the coefficient of determination, and you can see the correlation coefficient. Okay.